All right, today we're going to dive into the physics of vibration, a force that shapes pretty much everything, from the music we hear to the bridges we drive over. Let's get into it.
So, take a look at these two things. On the one hand, you've got this heavy-duty, complex piece of engineering. On the other, a simple weight on a string. I mean, they seem like they're from different planets, right? But believe it or not, by the time we're done here, you're going to see that they are run by the exact same incredibly powerful principles. The key to this whole puzzle, it lies in the world of vibration.
So to really understand that connection, we first need to get a solid handle on the fundamentals. Let's start with the big question. What even is vibration?
Well, at its core, vibration is really just a wiggle. It's any kind of back and forth motion around a central point, a point of balance we call equilibrium. It can be something huge and destructive, like an earthquake shaking the ground, or it can be something delicate and beautiful, like the vibration of a guitar string making music. Okay, so this slide breaks down vibration into two main flavors, and let me tell you, the difference between them is absolutely critical. First, you have free vibration. This is where you give something a single push and then just let it do its thing. Its own internal forces take over. A perfect example is pushing a kid on a swing and then letting them go. Then you have forced vibration. That's where an outside force keeps repeating, like you standing there pushing the swing every single time it comes back to you. Understanding this difference is really the key to everything else we're going to talk about. Now, to really get to the heart of how this works, we need to do what physicists love to do, simplify the problem. So let's take a look at the ideal model they use to study all this stuff. On the left, we've got the classic model, a simple block attached to a spring. Can't get much more basic than that. And on the right, well, that's how a physicist sees it, as a diagram of all the forces at play. You see, the block itself represents the mass of the system, while the spring gives it stiffness. The vibration, that comes from the constant tug of war between these two properties. And here's the crucial part of how that works. When you pull the block away from its resting spot, the spring creates what's called a restoring force. That's always trying to pull it back to the center. But the block has momentum, right? So it overshoots the middle. Then the spring starts pulling it back from the other side. This cycle just keeps repeating, and that's what creates that classic back and forth oscillating motion. So now that we've got this mental picture of this back and forth dance, we need a way to describe it precisely. And this brings us to what you could call the language of vibration. And this is what that language looks like. It's beautiful, right? If you were to track the block's position over time, you would draw this perfect, smooth, repeating pattern, a sine wave. And this simple graph holds all the key info we need. First up is amplitude. This is really just the peak of the wave. It tells you how far the block is moving from its happy place in the center. A bigger amplitude, that just means a bigger, more energetic vibration. Simple as that. Next, we've got the period. This is all about time. It's how long it takes to complete one full cycle, from the middle to one side, all the way to the other side, and back to the middle again. It's just the duration of a single wiggle. And frequency is just the other side of that coin. Instead of measuring the time for one wiggle, we're measuring how many wiggles happen in 1 second. We measure this in a unit called hertz. So a high frequency means a really fast vibration, a low frequency, a slow one. Okay, so we've got the language down, but now we get to what is maybe the single most important concept in all of vibration physics. Every single system has its own unique built-in rhythm. This is called its natural frequency. It's the specific frequency that an object just wants to vibrate at. It's not about how hard you push it or how far you pull it. No, it's determined by its own physical makeup, specifically its mass and its stiffness. It's part of its identity. Let's go back to our friendly little pendulum. When you give it a push, it swings back and forth at its own natural frequency. So what do you think sets that rhythm? Is it how heavy the pendulum is? Or maybe how far back you pull it before you let go? And here is the huge aha moment, a discovery made by Galileo hundreds of years ago. It turns out it's neither. The natural frequency of a pendulum depends only on the length of its string. A long string gives you a slow, low-frequency swing. A short string gives you a fast, high-frequency swing. The mass? It doesn't even matter. It's all about the physical structure of the system itself. So that's all free vibration, letting a system do its own thing. But what happens when we don't let it swing freely? What happens when we add that continuous external push we talked about at the very beginning? Well, this is forced vibration. An external rhythm gets introduced, and the system can't just vibrate at its own preferred natural frequency anymore. Instead, it's forced to follow the beat of that external driver. It has to dance to someone else's tune. And this is where all the pieces finally come together. We've got a system with its own natural frequency, and we've got an external force with its own driving frequency. This sets the stage for a truly dramatic phenomenon. So the big question is, what happens when the frequency of that external push perfectly syncs up with the frequency the system naturally wants to vibrate at? What happens when those two rhythms match? This is what happens. As the frequency of that external push gets closer and closer to the system's natural frequency, when we get that perfect match, the amplitude of the vibration just shoots upwards. Look at that curve. In theory, it goes towards infinity. Each tiny little push adds energy at exactly the right moment, causing the motion to grow and grow uncontrollably. This explosive phenomenon is called resonance. And this brings us all the way back to our train suspension. Engineers spend countless hours designing it to make absolutely sure that the everyday vibrations from the tracks don't match the train car's natural frequency. Because if they did, resonance could kick in and literally shake the entire train apart. But, and this was a really fascinating twist, resonance isn't always the villain. Sometimes, engineers actually use it as a powerful tool. A machine like the soil compactor is designed to do the exact opposite of the train. It creates a forced vibration that's specifically chosen to match the natural frequency of the soil, using resonance to compact the ground with incredible power and efficiency. So, the ultimate takeaway here is this. Resonance reveals a fundamental truth about our world. A series of tiny, perfectly timed inputs can produce a colossal output. From a singer shattering a wine glass with their voice to just tuning a radio, this principle is absolutely everywhere. And that leaves us with one last question to think about. Where else in your world do you see this hidden power of vibration at work?